Hello, here we present a solution to problem 6 of EGMO 2020. The problem is to find all integers m for which the sequence whose first three terms are 1, 1 and 4 and the subsequent terms satisfy this recurrence relation contains only perfect squares. We shall show that the sequence contains only perfect squares if and only if m equals 2 or m equals 10. So we have to look at two parts, if part and only if part, and we shall begin with the only if part. The main idea here is to consider the sequence modulo m minus 1. If we look at the first few terms modulo m minus 1, then we see that the sequence is 1, 1, 4, 4, 7, 7 and so on. To be more precise, we will get a2k plus 2 is congruent to a2k plus 1 is congruent to 3k plus 1 mod m minus 1. This is easy to see if we rewrite the recurrence relation modulo m minus 1. This means if p is a prime bigger than 3 dividing m minus 1, then the sequence will consist of all the residues modulo p. But this is not possible because not all residues modulo p are squares. So this means any prime bigger than 3 cannot divide m minus 1. So the only primes that can divide m minus 1 are 2 and 3. So let's ask if m minus 1 can be even. If m minus 1 is even, then a4, which is equal to 5m minus 1, also has to be even, and hence m should be congruent to 1 mod 4. But then a5, which is 5m square plus 3m minus 1, will become congruent to minus 1 mod 4. That's a contradiction because minus 1 is not a square modulo 4. Therefore, 2 cannot divide m minus 1. That means m minus 1 is a power of 3. So let's write m as 3 power k plus 1 and a4 as h square. Remember, a4 equals 5m minus 1. So therefore, we get 5 times 3 power k is h minus 2 times h plus 2. But this means h is odd. So h minus 2 and h plus 2 are co-prime to each other. Therefore, h minus 2 should equal 1, 3 power k or 5. And in these cases, h plus 2 will equal 5 times 3 power k, 5 or 3 power k. Then if we figure out what h is, we get, and from there what m is, we get m equals 2 in the first two cases and m equals 10 in the last case. So this proves the only if part. Now we actually show that m equals 2 and m equals 10 work. For this, we write m as t square plus 1 with t equals 1 or t equals 3 depending on m equals 2 or 10. And we construct a sequence which is essentially square root of an by defining b1 and b2 to be 1, b3 to be 2, and bn equals t times bn minus 1 plus bn minus 2 for higher values of n. With this, it's easy to see that an equals bn square for n equals 1, 2, 3, and 4. And for n bigger than or equal to 5, we get a recurrence relation bn square plus bn minus 3 square. And if we rewrite this and simplify it, this will equal m times bn minus 1 square plus bn minus 2 square. So by induction, it follows an equals bn square for all n, and hence the if part follows. This completes the solution.